Hey, how's everyone doing today? Who's all in the chat? It's open questions right now in office hours. If you are here right now, just got out of a meeting, had a little bit of lunch, need some more coffee, but who all is here? Sorry about the late start. Just had a meeting and finished the meeting, but who all is here? Anybody here? Am I the only one? Mubot's anyway. Aaron, how you doing? What are you working on, Aaron? I'm waking up Mubot in the background. Where's Mubot at? I need to set up an instantaneous Mubot button.
How are you, Aaron?
Mubot's here. Trace, good to see you. What's happening, Trace? Can we go over 1D for 474? Why not? That's on the new assignment, right? Let's go to that new assignment. 1D 474. Good to see you. It's almost the weekend. I mean, it's kind of the weekend, right? You know why I love the weekend? Like, I don't like, hey, Nathaniel, good to see you here. Good afternoon. I want to go eat. You know what? Never buy this. I love the weekend because I just eat like whatever I want. Not like crazy. Like I'm not gonna eat a bag of gummy worms. Maybe I should. But what was I gonna say? I don't know. I was just thinking we should make burgers this weekend. I'm just excited about that. And I'm like, that'd be really good. 'Cause you can't eat burgers every day. We're getting the assignments loaded up as Brian just thinks about what amazing food. Oh, Awake chocolate. That's what I was thinking of. Don't buy Awake chocolate because it's too good. Am I the only person, as we almost have the assignment loaded up, am I the only person on here who has had Awake chocolate, or has anyone else had Awake chocolate? If you've had Awake chocolate, you know what I'm talking about. Got the assignment downloaded. You know, let me close out of everything. No, I need these things. I'm going to need them later. 2 seconds. Closing down some files right here. I bet you someone in chat has had Awake chocolate besides Brian. Okay, we are good to go. Let's see here. Trace wants 1C. Sure, let's start here with 1D. We might have to do them in order. I'll take a look. And you've never had it. If you like caffeine, if you like chocolate, and you like caramel, get the Awake chocolate caramel. This is 1D for 474. Let's go take a look at it. Okay, 1D for 474. So check that out if you like chocolate and caramel and caffeine. As long as you're okay with having caffeine. Chocolate, caramel, and caffeine, you don't say. Awesome. This loads in. Make sure you have both in your working directory. So this is the... We'll go ahead and... Do we have some stuff up there? Oh, I'm in my package. Let's clear this. Go away, diet. I don't need a diet. I need this. Okay, so make sure... Oh, there's the diet. We have the diet anyways. So we have the Dozer data set, the product launch data set. We got some other stuff in here, some underfit, overfit models, just right models, some segmentations of data, some values, tons of fun stuff in here. Question 1, we're going down to 1D. So 1D to start, 1D. 1D says the results matrix below is set up so that you can record the RMSE on the holdout. Uh-oh, we got some stuff we got to do earlier. Holdout sample for all models and contained at most 2 predictors. The value in the row is labeled X2 and X3 with the RMSE, where X2 and X3 are used as predictors. The value in the row labeled X1 will be the RMSE on the holdout, where it's 1 and 1. So this is a little bit, it's a lot. Okay, so going back to here, it has the steps for doing this. We kind of have to start from the very beginning here. Because, so this is a start of this right here. You have to go through the steps. The product launch data set records the profit in the profit column of 652, and you can see it right there, 652 newly released products after the first few months after their release. A total of 20 predictors, these are the X variables right here, X1 through X20, may contain some predicted power regarding the model's profit. This is Y variable of interest. Throw a little Y on the end of this. The boss wants, that's what the boss wants, a very simple model. Don't put too many variables in it. Only at most 2 predictors, so we could use 1. A nested for loop is a great way to try out each combination of predictors. This is like all possible models right here. Run summary on the following to verify that 3 columns are this. Now, this is a huge hint right here. The way you're looking at the data right here is you're just pulling columns. You know what I'm going to do 1 through 10. Just only look at the first 10 rows. So what do we have right here? Now, be very careful when you look at this. Column 3 is what? What is column 3? So the code we're running, but think about this in the chat while we're talking through this. Column 3 is what right here? Now, I know there's a column 3. It's like column 3 of the original data set. column 3 of the original data set is what? What is column 3 of that? It's x2. So why is column 3 x2? Because column 1 is what? So quickly, kind of, I know it's this, but column 1 of the original data set is the what variable. Column 1 of the original data set is the what variable. Here it is one. Column 1 is what? Which is an important thing we're going to need to know while doing this. Very, very important thing. Very important that we know that column 1 is this. It's profit, but what is profit? And why it's going to have to be in every model. Column 1 is going to be what? It's our y variable. Great job, Trace, right there. It's our y variable. It's around 100 points. Meebot hasn't been giving out points lately. It's the y variable of interest. It's the y variable. And thank you, everyone, for following along. I can just say the answers, but if I say them, it's just like, what's the point? You don't learn it. So the first column is the y variable of interest. Just run that. Sure. That's it, is it? Sure. Using the random number seed 474, split the data into 50% train, 50% holdout. Verify that the summaries on the profit command are as provided below. So how do we split data into training and holdout? We need to sample. So let's go right here and go to train.rows. Now, if you're wondering kind of how to do all this, let's go take a look. A very, 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 very helpful resource in all of the code for what you're doing right here can be found right here. This right here, class examples using train, using Caret to tune models for predictive analytics. So you will see a lot of the code right here. Let's go ahead and just download this right here. We're just gonna make train rows. But if you go through here, there's train rows right there, and here's the train rows. That's a little more complicated than I'm gonna do. There we go, that's what I'm gonna do. There we go. This code right here, and there's a lot of code on this screen. We'll install those extra packages. We don't have them currently on this install of R. But we're going to take, there's a slide in the notes I used this. Yep. Bingo. Go to the notes, check out the notes, and use that. And working with Caret, I've downloaded it like 12 times, so got a lot on this computer. The train rows are simply going to be a sample of 1 through the number of rows. These are the things we're sampling from, and we need to sample from the rows in prod launch. Now, if you run this code right here, you just create a random sample, but we don't want the full thing. We want size is equal to 50% of the number of rows. Does that make sense theoretically what we've done right here? We'll put the seed on here in a moment. But now our random sample right here, or the train rows rather, are going to be half of the 652, something like that, 652, yeah. So we get half of the rows as training rows, but the train rows are now going to be used to go to prod launch. And where will it go in? Will it go in space 1 or space 2? Where will it go in prod launch? If we go right here and put train rows in there, where will it go? The train rows. So if we go here and call this train, and we call this holdout, where will it go for prod rows? Will it go in position 1 or position 2? Now that we've created, it'll go in position 1 exactly, because this is these are the rows we are selecting, and then what goes inside of here? It's kind of a quick answer. You can just do this. Here's the answer. I'll put it in the chat. Oh, I can't? Well, then I can't really put the answer. Oh, I can do that. There's the answer. I was just trying to hit enter, and it wouldn't let me put that in. Nothing goes inside of there. Now, the holdout is going to be the rows we don't select. And then once again, we're going to select all the columns. So it stands for take the row numbers we selected here, i.e. these row numbers, and then take the column numbers, take all columns. So we're taking only the train rows to put into the train. We're taking not the train rows to put into the holdout, and we're taking all the columns right here. We need to put set.seed false74. That's going to control the randomness. There we go. And then let's see if we have the same data. Cross your fingers. A summary right here of the profit column on the train. And look at that. Beautiful. If you have issues with this, please tell me. There are ways your randomness can be set up. Good. I was worried. Whoo! Is that making sense there, Aaron? Aaron, you might have already done this. Once again, the slides have tons of answers and show how to do all the code. So please, 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 please look at the slides. Really great resource for all the questions we're asking right here on like how to make a train, how to make a holdout. And you're just taking a certain percentage of your rows and holding them out. I personally hold out like 25, 30%. But Seaver would say divide this into 4 holdouts. I guess it's a smaller data set, so you might need to hold out more, like a larger percent, because you have to have enough that your holdout doesn't have a unique structure to it based on some outliers. So I don't know. Theory of what to do is the hardest question. All models are wrong. Our model's going to be wrong. Hopefully we'll get a useful one. So now we get to C, which was, I think, Trace's question about 1C. This one right here seems a little tricky, but the issue is we have to build a model first. Who knows how to write a linear model? And this is where it gets a little bit weird. Who knows how to write a linear model right here with 2 variables? Like, write the basic form of a linear model with 2 variables. This is where it gets a little bit like, what? But no, this is the easy part. Write a linear model with 2 variables. Write a linear model that has 2 variables in it. So at this point, all we want is a linear model that has 2 variables in it, like in a basic form. Going back to BAS 320 right here. Write a linear model. There we go. Great answer right there. And Trace, that it would technically be 1 right there. So we're basically going to do the same thing. Trace put linear model, y tilde, and then I'm going to do x1 plus x2, comma, data equals, and then what data equals. We can store this object because it'll create something. It'll create a list right here. And we can store it into the LM function. So, I mean, not the LM function, the LM object. So it'll create something. We can store it into an object. And that's what the left arrow is going to do right there. So the linear model right here is going to predict profit. But this is where things get a little bit weird. We want these x1s and x2s to change interactively. We can do this, and the answer to how we do this is going to be based on how we took our data. If we go here and give data equals this, we're giving it the y variable, x2 and x4. Remember how we saw earlier this was x2 and this was x4? If you don't believe me, I think I still got it in the copy paste. This right here is, oh my gosh, that's what I'm going to take all of them. This right here is x2 and this is x4. And that's what we have going on right here. Oh no, Jason's calling. I'll call him right back. Oh man. Wait, dang it. I was just in a meeting with him. He's going to feel so bad. I'm not ignoring him. Dang it. He was in my meeting. He's my studio producer. Jason, shout outs to Jason. I'm sorry. I'll call you back, Jason, right after this. He was in the meeting for stuff we're doing for online stuff. Good. Lots of amazing things coming down the road. So how could I then take all the columns? What should I change this to? What suggestions do you have? Because right now, I have that the data is only going to be this data you're seeing right there. So that's the data you're seeing right there that I have. So then how could I take all like x2 and x4, but I don't want to call them? Exactly, tilde dot. And let's just make sure it runs. Let's look at the model and see if we got what we want. And we got what we want. Is this making sense right here? And then look what we can do. Let's start out here. A very good place to start. We've now taken x1 and x2. Oh my gosh, 100 points Trace right there. I was just seeing if you were paying attention. Totally not an error on my part, just seeing if you're paying attention. Good job paying attention. So, you are very, 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 very correct, hence the 100 points. And so right here, we have x1 and x2 predicting profit on the training data because we make our model on the train. So now let's go here and let's say, what if I were to do this right here? Or this right here? Or this. Do you see it? Do you have any idea what we could do to this variable? But I want to get something first. You might be seeing what we're going to do as we move through the variables. But let me go to the summary. And you might not know this, but the summary is a list. And nope, it's not spelled like that. Nope, it's not spelled like that. Let me store the summary and see how it's spelled. Summary. Sure. Summary is a list of 11 things. And not well, I gotta do it the residual way. I don't want to do it the residual way. Just R square. I swear it's in here. We're gonna loop through it exactly. That's what I was demonstrating. Great job right there. Excellent work, Trace. That's exactly what we're gonna do. I swear it's in here. Is it sigma? Let me look at the value. Yeah, I think it's calling it sigma right there. And that value is sigma right there. Should be the RMSE. And let's go down to it. Check to see if it's sigma. So we should be able to go in and do $sigma on this. And we are getting 3.833. And that's what's rounding right there. That's the residual standard error, which it calls sigma. I prefer to call it residual standard error. So that is the uncertainty in, or the typical miss the model makes, the uncertainty in the residuals in our model. And so we can get this by running sigma right here. So now we just want to store this. We'll eventually store it. But, right, verify that summary is below. Oh, so we need to use the right variables. Okay, let's go do that. Sure. And let's look at the summary. Here, I'll hashtag this out because I want it for later. There we go. And it looks like we have the same answers, so we're good to go. So now we are going to loop through it, and it explains how to do it. Because we have a unique scenario right here, and I hate all the code. Just the way it looks. Oh, look at that. Oh, because we're doing it on the holdout. Yeah, so we don't even want it on the, yeah, makes sense. So let's go down here, and let's take our code. We're not even going to use that sigma. What am I doing? So with this code right here, we do have a sanity check on this on your matrix. Let's go ahead and make the matrix right here. Matrix is made. So now we have a results matrix that exists with all the row names and all the column names as they exist. We're now going to populate those positions. But first off, we have our model. How could our model make predictions on the holdout? So how could our model make predictions on the holdout? What function would we call to make predictions on the holdout? Once again, we're writing the code that we're going to write before putting it in a for loop. How can our function make predictions on the holdout? Hint, I'm giving away the answer by asking that. How can our function make predictions on the holdout? How can our function make predictions on the holdout? What function could we call? It's listed for you down here. Sometimes I wish, oh, maybe it's not. How could we make predictions on the holdout? What function would we use to make predictions on the holdout? Some 320 right here. No, we could use like a k-means algorithm, but that would do like a clustering scheme. And so we're not looking to cluster right here. We're looking to just use a model to make predictions. So we're going to use a model. We're going to make predictions from our model, but we don't want to make it on the original data. We want to make it on new data equals holdout. And here's the predictions on the holdout. So this is how our model, I did new date. I thought they looked the same, and now they look different. So these are predictions on the new data. These right here are the actual values. Hence, it's showing down them here as y predicted. I said actual because it's in the next step. These are the predicted values right here of the y for the holdout. What are the actual values of the holdout? Don't go crazy. Where can I get the actual values of profit in the holdout? Where can I get the actual values of profit in the holdout? Where can I get the actual values of profit in the holdout? Don't go crazy. Promise this is not crazy. Nothing too extreme right here. I just want the actual values of the profit in the holdout. All I want to see is just what the profit was actually in the holdout. Like, just go to the holdout and look at profit to get the true actual values of it. Well, but I just want to look at them. I just want to see them. I just want to know what were the values of profit in the holdout. So I just want to know, like, what was our value of profit in the holdout? What was it? Like, just find those values. What are the values of profit in the holdout data frame? So another way of phrasing it, what were the values of profit in the holdout data frame? Which is the actual values. So we've got what we predicted them to be via our model, and then we have what they actually are. So how can we look at the actual values of profit in the holdout data frame? So we want to go to the holdout data frame and then look at the vector profits. Yep, that's it. Great job. Yep. That's the actual values. And then what am I finding right here by doing this? I'm doing it in 2 steps. What are we finding right here by doing this? I don't want to store in question mark, question mark, question mark. What am I finding right here by doing this? What is this? Here's the actual values. Here's the predicted values. What are we finding? What are we finding right there? I'm going to do it in, it doesn't have this step below, but I want to do this. That's the what? Here's the actual value. Here's the predicted value. What are we finding right there? Basically, this is what we thought it would be via our model, and this is what it actually is. This is the difference between what it actually is, and this is what we thought it would be. There's the difference between the two. The residual, exactly, or the error. No, I wanted to hear residual. Actual minus predicted is residual wrap. That's the error, but I'm writing it error because I want to store RMSE as square root of the mean of the error squared. Does this make sense right here? So this is the root mean squared error. And there we go. And that's the RMSE. So now, just the way I've written it out makes a little more sense to say, okay, that's the difference between what the model predicted and what it actually is. And then we can just take that error and do the root mean square error of it. And there we go. Here's the RMSE. So now we really get down to where would we be storing this? And we've got right here that this needs to be stored into the results matrix. And we could do that right here. Where do you think we should store this? Any ideas on where we should store this? Any ideas on where we should store this? Where should we store this? Where do you think we should store this? There's a hint up top. What should I and J be? It doesn't matter which order we do. So in the results matrix, where it says store into IJ, but I should probably put places. I'm just kind of doing an example, like doing, yeah. Well, not 1 through end call. Well, I see what you're saying with the loop. Don't worry about the loop yet. We're doing the loop by not doing the loop right now. We're just going to like run it so it works. Well, we're going to go through that many rows and that many columns. Well, kind of very close. We'll do the loop here in a second. But where should we store this into? Which will give us some insight of what we should do right here. Where should we store this into? Like, where should this value be stored into? Where in the results matrix? Like, the results matrix looks like this. It's a bunch of values. Where should I put this object right here in this matrix of things? The combinations of the x's we're doing. Where should this error for this model created up here be put into this matrix right here? Like, what position in the results matrix should have the miss that this model made that was made from, and we got to be very careful, this was made from x2, x4. Well, not 1, 1 yet, because this would be a model that only has x1, x1 in it. So we want to put this one, be very careful. This is where a mistake might happen right here. Do you remember what we saw originally with this data? That this data is using x2, x4. So shockingly, we wanted to go there. So let's take a look at the results matrix again. And why am I putting it here? Can you explain to me why it went right here? Why did the model go right there? Think about why the model went right here. And correct. Because if you take a look at what the training data was on, then you'll see, let me clear it out and write it again. You'll see that we're using x2 and x4. Does that make sense? Is this making sense, Aaron, right here? Like why I chose to put it in position 2, position 4? Because the matrix is the combinations of variables being used to make the model. And we see right here, x2, x4 were the variables used. So that's the miss on the holdout using x2, x4. Is this making theoretical sense? Like why I put it there? Because x2 and x4 were the variables used. And this is going to be how the model does on different subsets of variables, whether we do like x1, x5, x2, x8, x3 as the only variable in the model. And that's where we're going to have an issue. The issue we're going to run into is right here, because what kind of model is this? Explain to me this model, just visually speaking, what is this model here? Take a moment in the chat and explain to me what's going on with that model. So what's going on with that model right there? What's going on with that model? Just look at its combination. And this is where our code has to change, and we're going to do something slightly different. What's up with that model? Any ideas? X3, X3? Well, currently we have not put a value in. So we haven't filled, we're going to fill this matrix with the value of RMSEs, and then this model will be filled with a model that is X3, X3. So what does it mean that this model will be X3, X3? Like this model we just did was X2 and X4. Hence, when we looked at it, if you remember a second ago, it says 3 and 5, but that's because X2 is in 3 and X4 is in column 5. A little confusing right there. And that's why we sorted in position 2, 4, because it was a model built from X2 and a model built from X4. But what about this model? What is this model built from? What is this model built from? In this position in this matrix, this model's RMSE will be the model of how a model built from what? Hint. Works on the holdout. This will be how a model works on the holdout that is built from what? You got it right there. Well, it's only going to have one variable. It's a model that's only built from X3, but right now we're grabbing two variables. So let's make a model that is only built on X3, and we don't have to change our code much. To make a model that's only built on X3, and I want you to take a look at the data right here. This is only using X3. Does that make sense right here that this is only using X3? So we're going to do the same sort of steps right here, but when we get to the bottom, this will be what right here. Be very careful. Be very careful. What will go right here? And so we wouldn't select 3 twice. We would just take 3 one time. So no, I think that's where the issue can be, Trace. What am I doing decomp when using the project sales data? When I'm using the STL train, it only says univariate series are allowed, struggling to get it to univariate. You might send me what you currently have using the project sales. Let me take a look. I'll do that here next, Ben. Great question. So it can only take like a 1 vector univariate time series. If you do that, we're going to probably next week start talking about some dynamic time series, which can take the XReg. So that's the X regression. So if you want to do that, you can start looking at some dynamic time series, which are going to include regression models in them. So kind of fun stuff right there. Let's plan for next week, including X variables, extra sort of variables in your model. And so right here, but if you send me the project sales data, if you send me what you're working with, I'll take a look. So right here, we're going to go into 3, 3, and we're going to store the error. And let's take a look at the results matrix, make sure it worked, and take a look, we've done it. Is this making sense right here? That we've stored into results matrix X3, or a model only built from X3, which is in column 4, because remember, if you look at the data set, you can see that column 4 has X3 in it. That's where people usually get confused on this. They're like, well, wait, you typed 4 up top. That's because column 4 is X3. So really, and the code down here kind of walks you through this, but take a look. We want to go here 4, and I think this is what Trace was pointing out. I will go 1 through the number of rows inside of the train data set. And then now we will go 4. J will go 1 through the number of columns. Wait. We just do number of rows again. But actually, yeah, we'll be fine. And call of train. No. We need to do number of calls still. My brain broke. And what we should do is I want this to basically go 1 through 20. I could just wrote 1 through 20. Let me make sure both these go 1 through 20. They do. Or they go 1 through 21. Just thinking. Oh, let me just start right here. There we go. Fixed. And yes, this will go through all 20x variables. Genshoot, awesome. I'll check that next. You got it, Ben. So now this will go through all 20 variables. And then we have to think. If what is what? So look at this scenario right here. When will we run this scenario? Can you tell me when? What is the condition we will run this scenario right here that we just ran a second ago? When will we run this scenario right here? Take a look at this right here. And when will we run this scenario right here, which is the code I have right here? When will we run this scenario? When will we run this scenario? So when will we run this scenario right here? So I'm just looking for the condition. As we go through, we could do it in the matrix too if we want. We just needed 1 through 20 basically, or 2 through 21 works too. So when, because this is I now, and this is J. So when will we run this scenario right here? When will we run this scenario? Any ideas? So we have x3, x3. So what would that mean for I and J? Exactly. So if they're the same. So if I equals J, and we're just going to take the code we have right here, and then we have to change it so it works. We're going to open up the if and go inside of it. Really? There we go. Control I, Command I, fix code. You can also go to code and reindent, reformat. Those will help. And it's Control I right there. So now, if you take a look at this, this is going to be, let's reformat these, because these are what are going to have to change. This right here is going to be I minus 1, because it's going to start at 2. And this right here is going to be J minus 1. And this right here, up here, is going to be simply I or J, doesn't matter. It's just going to be the variable we're selecting. Remember, it is going to start on the second one, which is the first X. Is this making sense, right? What I did right here, all I did was put in my placeholders so that it stores into the result matrix right here, which we did a -1. If you look at the way we wrote it previously, if this is 4, then these are 3. So when this runs 4 as I, it'll run 4 minus 1, 4 minus 1, which will get us 3, 3 right here. So just going through, if you think about what I is becoming as the loop runs, if I and J are both 4, then it'll say, oh, only run this model here where we have just the I being used. It'll run I is equal to 4, which will store right here into this spot, or excuse me, which will grab the third X because it's in the 4th column. And then when we get down here, it'll do 4 minus 1, 4 minus 1 for the row column position. So now we just need to put an else right here. And the else is going to be the code up here, which is going to be nearly identical. And we're inside the else. Let's reindent line. And now when we do this, this is going to be I, and this is going to be J again. And then we just do the same thing. I minus 1 and J minus 1. And then we cross our fingers. I think we've done it. There were 50 warnings. We don't like that. Might have done it. Don't like the warnings. Ooh, something doesn't look right. Something doesn't look right. We're getting multiple matrices, it looks like. Or maybe... Let's go look at the answer, or the check for it. No, maybe it's all right. Well, I'll be. Get some warnings. Well, I'll be. That's got it. So there we go. We've basically gone through and looked at all these models, how they work on the holdout. Is that making sense right there, Trace? As we did the process, I was like, something broke. And I was like, I guess not. What are those warnings it gave me? I hate it when it says warnings and it doesn't tell you what they are. R is so nice like that to tell me there is a bunch of warnings. So wait. Use warnings to see the first 50. Tell me about my warnings. In prediction LM, prediction from rank deficient may be misleading. LM. Really? Man, it's super mad about those models. Is what it is. Oh, it says that. Fun times. You know what you can do? Watch this. Suppress warnings. Now, no warnings. I was just not having a clue of the loop part. Yeah. This is a tough one. This is a tough one. I mean, this is like super, like it's a lot. It's a lot. And I think the hardest part is putting everything inside the loop, getting it all to work, because if something doesn't work, it just all breaks. And it's like, well, I can't get the values out of it. So I'm kind of glad to do this one here, which that's a bit of the assignment. Going through some interpretations at the end. I think this is nice and easy at the end. We covered this a lot today because I knew this was on here. Like I knew the other one too, but I just haven't done it in a while. But this right here with the cross-validation, pretty easy. Yeah, that's a pretty tough problem. That's probably the toughest on here, which now the answer's out there. So just make sure to practice, go through the theory on this. That 30-minute talk is going to do a lot more than just writing down the answer. Understanding why we use a holdout, why we use a train, and then I'll let you do the which and stuff on it to see which one does the best. And it's got the arrand equals true on it. I always make a typo on that error. On that array index equals true. So the reason we use array index is because it's a 2x2, and that tells you, and due to the symmetry of this, because that's x2, x4 in the ij variable, or in the ij variable x4, x2, either which way, it's still the combination of x2 and x4 give you the lowest error on the holdout. Probably a lot of these are similar though. Let's head back to the main screen. Let's do this. Okay. So we have another problem right here. Let's go look at Ben's. Time series for group. Oh, here we go. Might not be able to show it. It's the... So let's see right here. Oh, wait. Okay. Which line is it you're trying to decomp, you said, Ben? Awesome. So Ben said he's trying to decomp. STL of the train. Okay. So it looks like... All right, here. Let me clear out everything I have. Okay. Let me look at where the train was created. Shouldn't get mad about that. Okay. It's working. You do have a frequency in there. Something's happening later on. Scroll down to the decomp. Yeah. Let me see right here. Let me look at your train. And I'm just running a few things in the background here. I'm trying to not show group code. It is working. I think you're doing something to the... So it says only univariate. Yeah, you're right. Only univariate series allowed. Why is it thinking it's not a univariate series? The MSTL works. So I think it's because there are 2 columns in the train data. Are there 2 columns in the train data? Let me look at using just the original time series data. And let me see. MSTL works. If you want to do MSTL, that works. This might work. Let me go back in time. Okay. Oh, that works. Fix it. Okay, it's being weird. I hate it when it's being weird. Found the solution. So for the take home, there are not specific problems to do. Correct. Basically, I wanted to make it like a job where it's like, we need you to analyze data and we need you to explain your process. And so you need to go through. Yeah, no, I got it working with STL. I'll show you how to do it. I don't think it's too much to show this. So we have right here, just taking the first column right here. The decomp is working with STL. And you got your decomp. You should be able to auto plot the decomp still. But all I've done is taken. But I do want to point something out here. What's happening to your sales right here? I do want to point something out, which make sure you notice this. What's happening to your sales right here over time? Your profits. What's happening to your profits over time? Correct. That is correct. Profits are increasing. Profits are increasing. But they are increasing. Like I'm the person at the company. I say, yeah, my profits are increasing. I promise you I've been watching the sales data over the years. I've been here since 1950. It's now 1990. I've been here 40 years. I started this company when I was 20. I'm 60 now. Profits been going up yearly. Profits have been going up yearly. I can promise you that. I'm not making things up. I looked at the numbers. I know how to read numbers that are going up. What do you think? I can give away the answer. I'll help out with this because I want to make sure this is not too big of a change, but it's a major error, which I'm hoping. Well, do you think, let me ask this. Do you think when people send you, I wasn't trying to throw a big trick, but I was trying to throw like a make sure you catch this type thing. The big thing about profits going up or definitely should be noticed. And you can always ask questions. The data's real. What do you think's the issue? There's a quick way to work with it. There's a quick way to fix this. The data's real. I haven't said any lies. I just sent you our profits. But I did communicate that the profits have been going up, which is a big thing to catch that I kind of wanted to be something we got to make sure we notice because not every problem is going to be like we get the data and it's perfect. We don't got to do a lot of data cleaning here. But what do you think's the issue with your series up there? No transform, no transform. Your profits are going down, and I'm telling you profits are going up. So what's the issue? You were close. I just want you to get it. I'll say it here in a moment if you don't get it. Don't worry. Don't worry. I'm throwing out 100 points. I guess one could say you might need to transform it, but it's not like a log or something like that. We're not going to log it. Don't worry. This wouldn't be like it's like a not a time series question almost. If you believe profits are going down, but I've communicated to you profits are going up, you might be looking at it what way? Because I've definitely communicated profits are going up, but you're communicating right now profits are going down. So you might be looking at it what way? So this is because I think sometimes we think too much like what we've learned in class, but then this is more like reverse. Exactly. So there's a really nice function. So one, you could just code it differently. Basically, we need to go up here and we need to go where the variable's read in, and we need to go to the time series and go to the reverse of it. And you can write rev on it. That reverses the vector. That's just one way to easily do it right there. There's about 1 billion ways to do it because there's always so many ways of doing stuff. This should fix it. Should. Didn't fix it. Let me go look what's going on right here. Does it not like the reverse of the time series on that? Or the reverse of the vector? Let me go reverse it right here. TS, storing to rev TS. That should be reversed, right? Is that not the reverse function? Yeah, of an argument. That should do it. And that should fix it. One would think. So let's clear that. Let's run the reverse. Still showing it going down. The train window is ending at this. The holdout is starting at this. Why is it still reversing it? Or not reversing it? Why is it still? My brain is just not working. Is there still something stored here? Let me see. Let me fix this up. Read in the time series object. Time series object read in. And let's go here to time series of the time series object. Let's go here with start. Oh my gosh, go away. Start equals. Can we not just reverse this and keep it reversed in the brain of R? TS2 is TS, but reverse TS. And let's look at TS. That has the smaller numbers. Let's look at TS2. Ooh, it's not reversing it. What are you not reversing my vector for? I really thought, is it not reverse? 2 seconds. Reverse order vector in R. Reverse elements, rev. I think something must be taking the rev and using it. That's base R. Am I going mad, everybody? Because this is not reversing it. It's supposed to reverse it. For this, you could do the time series cross-validation is one way of doing it. We were doing that today in class. Oh, you're talking about, yes, for the BAS474, for BAS474. I literally made models for this. I can't think. Let me see something. Let's let me go to empty cars. There's that vector. That's the reverse of that vector. Time series. You know what? What in the world? Why is reverse not... I think it's the way it's reading in. Read.csv. S.vector. I think... Let me look at what TSC is, because that's weird. It's reading in as a data frame. That's part of the issue. So... S.vector... Still reading it as a data frame. What? Yeah, you might do that. I had my models working and everything perfectly fine. So 2 seconds right here. We're just not reversing it, which is weird. If TS is reading it as a... Oh, there we go. Boom. Oh, my brain is fried. Okay, we got it fixed. Here it is. Let's grab this. Horrible variable name. Okay, so watch this. You ready? Sometimes I do something a week ago. No, brain just doesn't work. We go right here, and we don't take the data frame. We take the rev of it. There we go. Now let's look at the data, and there we go. Sales are increasing. Let's run the vector. There we go. It's the data frame. Just grab. There we go. Boom. There you go. Cross-validation in R. Yeah, which part? 474, 475. 474, 475. And now the decomp is working. Yeah, so that was actually and now we don't actually, so here's the pro 2 part of it. Here's the best part about this is it all kind of went back to, so Ben, do you see this right here? So the whole problem was kind of going back to the issue. Is this making sense, Ben? That the whole problem was going back to that you were using a data frame to make a time series vector. It seemed to be working on some things, but we don't want to take the data frame. We want to take the variable inside the data frame. So that's why I couldn't reverse the data frame. And I was like, okay, so that's why it's not reversing, because it was a data frame. We want the vector inside the data frame to turn into a time series vector, but you actually want the reverse of the vector. I was like, why are my codes not working? It's because I was trying to reverse the data frame, and the code doesn't work on a data frame. So that's when I checked my object. If you remember from all my work, I was like, so what object am I working with right here? And then I went and ran and it worked. So now everything's working. The reverse is working. And down here, the decomp is working because this is no longer a data frame. A little tricky right there because, and that's why when I went here before, I pulled the column out of the data frame. Yeah, it's always something small. And then I kind of just like went down a wrong path, but that's how it goes with coding. I need like a boom. So yeah, we fixed up some little errors right there, but feel free to ask questions on this because I hope if other groups are seeing this, I feel like today's the day. So I want other groups to see this right now and being like, oh, it's increasing. They're not always going to send you the data the exact way when you load it in. It works because sometimes you load it in and there's things going on. One error leads to another. Yep. And so you got to make sure you take the vector out of, that's just one way right there since it's given to you as a data frame. Let's go do, I think, Trace had a question right here. Can you go do cross-validation? Or which type of cross-validation, Trace? Let's head back to the main screen. Oh, stretch time, stretch. Stretch on these Fridays. What kind of cross-validation are you wondering about inside of our Trace? What kind of cross-validation? Time series or 474 cross-validation? Time series or 474 cross-validation? We're going into more cross-validation 474. Will the project ask for cross-validation? Yes. Let's take a look at that right there. So I was wondering if you... Yes, of course. Definitely. These notes right here. Let's go take a look at these notes. Here we go. Back to the main screen on cross-validation for the project. Here we go. This right here is a mammoth set of notes. And when we do this, you will find answers to pretty much everything you ever wanted to know and more within these notes. So what we need to do first is we need to set up our train control. Let's go over here to train control at the very start. So many train controls. The train control is how we will set up our train control right here, which is how we are training our data. So we'll set that up here in a second. Let's go to the fit control because that's where we store it. And go to our fit control. So many things. Let's talk a little bit about fit control to start because we showed the different versions of it. Here you go. Why do you think... Let's get through that way. Why do you think there's two different types of train control right here? Why do you think there's two different types of train control? Just pause for a moment and think, why do we have two different types of train control? Why would we have two different types of train control? It's almost like there's two concepts we learned in the first week of Stat 201, which carry through to all of statistics. I tell my 201 students, like, you have to know this. Why would we have two different types of train control? And you might say, well, isn't that a fit control? Well, that's what we're storing the train control object into. So train control is a function that creates how we are going to train our data. And today we talked about the cross-validation process right here. So that's the k-fold cross-validation process. This is the repeated k-fold cross-validation process, which gives us an ability to create uncertainties. But why do we have two different types? Bingo, Trace. Bingo. Down here, you're looking at categorical. And up here, you're looking at quantitative. So quantitative and categorical, depending on what type of thing we're doing. What type of variable is the y? And this is a quantitative y, and this is a categorical y down below. So what do you want to do? What kind of model? Do you want to do a logistic? We could train a model to predict. Do you want to predict someone's gender or someone's weight? What would you like to do, Trace? Predict someone's gender or predict someone's weight? Your call. Which will be similar to what you're doing. Predict someone's gender or predict someone's weight? Which one would you like to do? Predict gender or predict weight? Which one should we do? Which, if we're going to predict weight, then we'd go up here to these. If we're going to predict gender, we're going to go down here to these. Gender will work. Let's do it. So the methods down here, I don't usually fit to accuracy. I fit down here to the AUC ROC, which we'll talk about more when we get to it. The AUC ROC, we need the class probs equals true. Also the 2 class summary factor right there. Let's open up a new sheet. And we're just going to make this look nice and pretty right here. I much prefer it looking this way right here, where it's a little easier to see what's going on. All these are our different arguments right here. This stands for we're using cross-validation, which we talked about today in class. That's the k-fold cross-validation process. Go back and review if you have questions. The number right here is folds, which means it's k-fold 5. Do we still have those notes up? We don't. That means we're putting 5 different sections where each time the validation portion will move throughout. The summary function equals 2 class summary. That's how we get the AUC. Class probs equals true means it's categorical. So if we don't turn this on right here, which you can see in the code in the previous thing, if you don't have your summary function equals true, or 2 class summary, excuse me, you will not get the AUC. You'll get accuracy. And I prefer AUC. AUC is the probability we give the yes class a higher probability, or the percent of time we give the yes class a higher probability than the no class. It's just ordering things correctly, putting the things that are the yes individuals, the ones we want to predict, at the higher levels of probabilities than the no's. So correct ordering matters here. Not the probability percentage, but rather do the things that are what we want to predict. Like we want to predict if someone's going to purchase, do we give them high probabilities higher than the no's? So the fit control is made. It's just going to be an object stored in the global environment. When we call the train function here in a second, we're just going to do tr control. It's got a capital, watch out. We're going to do fit control. We're not going to do this yet, but this is going to be what we're going to put in as an argument within the train function. So let's go here and choose. We'll do the GLM net. Let's go back. And let's do a GLM net. There's a GLM. And vanilla linear, regularized linear, regularized, nearest neighbors. So many good stuff. All these topics we'll be covering right here. And let's see. We should be able to do it. Just thinking right here. Vanilla logistic. Here we go. I don't want to do vanilla logistic. Let's go and grab. So this is one of the great things about this is number 5 standard. You can decide. You can use or decide. It shouldn't make that big of a difference. We'll grab all this code right here and start going through it. Explaining what it does. Really good notes on this. So much going on right here. Okay, let's start from the very beginning. Oh my gosh. Oh, this has got nearest neighbors. Well, nearest neighbors on here. Okay. Let's go through this bit by bit. And once again, this is such a great resource here for you. So what is the GLMNet grid? Do you remember alpha and lambda from today? Do you remember alpha and lambda from today? Alpha and lambda were a big topic today. And alpha is going to be the percent we mix our lasso and ridge regression. Lasso and ridge are the way we penalize ourselves in regularized regression. So we're going to penalize, the way we're going to mix them, because it's alpha, is we're going to start with a 0 mix, which I believe is all lasso. It's all of 1. And alpha is between 0 and 1. So it's going to go from 0 to 0.25 to 0.5 to 0.75 because we're going from 0 to 1 by 0.5. So the next parameter we have right here is lambda. And lambda is going to be a sequence of values. And we're making lambda very small. So lambda is going to be values like 0.1 and 0.001. You can look at the values of lambda right here by taking this code and seeing that these are the values of lambda. And this is the way we penalize ourselves. So we're looking at different penalties we will put on the regularization parameter. Now, we saw this yesterday. Expand grid is going to create all the whats of these parameters we can pick from. The expand grid is simply going to create all the possible combinations. Does this make sense right here? That these are your combinations. Like you can do an alpha of 0 with this lambda. You can do an alpha of 0 with this lambda. And these are just the combinations we can test out. Like we're just baking different cakes right now. We'll be like, here's my cake with an alpha of 0 and a lambda of 0.1. Well, I tried another cake with an alpha of 1 and a lambda of 0.01. And we're going to see which one of these cakes tastes the best by making a model here. Setting the seed so randomness is the same. I like my randomness. And let's go ahead and remove this off right here. A little partiness right there. Let's go through the code and see what it says. So let me put that back on the same line. What do you notice about the start, which is so beautiful? What do you notice about the start of the train function? What do you notice about the start of the train function? We're basically done. It's making sense. Awesome. What do you notice about the start of the train function right here? And do we have our data for it? We don't have our train data. 2 seconds while you think about what that's saying. I'm going to make some train data. Data, survey 9, 10, go 10. 10's nice, doesn't have missingness. Survey 10. Let's go here and do 1 through sample. And we got to take the same thing. Train rows. Train.rows. Sample 1 through the number of rows of not sample. And sample what percent? 60%. And let's see if this found my train rows. Oh no, what'd I do? Is that not a vector? That's a vector. Oh my gosh. There we go. And now we take these train rows and we take all the columns. We store this into train. And then we store into holdout everything but that. Little chill music. And so now we have our train. Now we have our holdout. And now we go down here. So you have your y variable with all your other x variables. Correct. Correct. And you might say, well, aren't you taking too many then? So Trace, someone would say to me, Brian, you shouldn't use all your x variables. What's going on up here? What's going on up here, especially with this? What is going on there? Lambda is doing what for us? What is Lambda doing for us? Correct. If I look at my train and my holdout, to go back to that code right there, the train and the holdout, the train's going to have 60% and the holdout's going to have right here. So we could actually, set a parameter up there, but yep. Excellent work right there. And then why, if someone said, well, you're including all your x's? And I'd say, no, I'm really not. I mean, maybe in some sense they might be utilized to some degree, but what is this lambda parameter doing for us right here? The lambda is the penalty we have for taking information from our x's. So at a higher lambda, what's going to happen here? At a higher lambda, we're going to take less information. So I'm making available to this all the x's, but it costs the model to use them at higher values of lambda. As lambda's closer to 0, it probably will use all the x's, which maybe would be good, and that's just regular old linear regression when we just throw everything in a model. So we're going to get penalized exactly. That's the penalty. So I'm giving it access to all the x's by giving the y tilde dot, but it might not use them all. The tune grid is our grid that we gave it. That's the glmnet grid. That's all the values it'll try. The fit control right here is just basically going to output the AUC. And the preproc, what do you think the preproc does to the data? Because we want everything to have an even playing field. So now that we know what all this, I want to pause right there, but what do you think the preproc center, like we take the distribution, we center it, and then we scale the distribution. What do you think the preproc does to the data? You got to trace. Lambda is the cost of regularization, like the penalty, like how much weight we put to the regularization. Higher lambda means more regularized models, which are going to go simpler usually and have better connection between how they work on the original data and how they work on new data. But we might get a model that just is kind of bad. Like it might work bad on original data and bad on new data. Might be high bias, but low variance, but just bad. What does the preproc do? The preproc is going to do what? The preproc is going to do what? It centers it. Well, kind of. The preproc is going to take every variable and turn them into z-scores. So the preproc is just turning things into z-scores. Error object y not found. No! Now it's found. Accuracy was not set. That's fine. I'm worried about this one. That's fine right here. The metric accuracy was not set. RSC will be used instead. That's perfectly fine. That happens. Warning message, function, kind equals null, normal kind equals null, sample kind equals null. Non-uniform rounding sampler used. Sure, you can do that. Not worried about that. Now let's look at which model we'll pick, and it is tuned on AUC. And here's our model. Ooh, wow, amazing. Which model looks to be the best right here? Which model looks to be the best? It looks like we want moderate regularization, and we want to go really all for one. Which one is that? That's the red winning out right there. You know what I'm going to do? Here's what I love to do. Is I'd love to go in here and change this to by 0.2 and change this to by 0.1. Rerun it. Takes a moment longer. And what have I just done? Watch my graphic change right here. And now my graphic has a lot more unique spots to it. And I might even try to zoom in on this area. Can I turn this into a ggplot? Ooh, that'd be amazing. This will make my day if it ggplots. Library Plotly. And let's go here and go to ggplotly. I do not know if this will work. And there's only one way to find out. Nope, doesn't like it. Default plot in R. Well, maybe. What type of object is this? GLMnet. It's nice that the default plot works. I bet you, and I want to find this out. Plotting train output in our ggplot2. Viewing ToonGrid ggplot2. Visualizing. I would think that someone has some stuff on this. I've seen some stuff. ggplot. Okay, wait. Are they saying just put ggplot on it? Well, I'll be. Yep, well, there you go. Just throw a ggplot on it. It takes it. And now we can go over here and do that. And there we go. So this is going to help me view a little bit better. But there we go. Oh, you don't understand? Oh, no worries. So this right here, when you look at this graphic, which we're kind of getting crazy on this, we'll zoom in on this portion. I've really made it completely crazy in here, but you really want to just look for the best value right here. So if I zoom in on this trace right here, it's telling me what should I use for my model? Because this is the highest point. We want high ROC. ROC is the percent of time we give the yes class a higher probability than the no class. So what do we want right here? What should we use? This is the regularization parameter on the bottom, which this right here is your lambda. This is the lambda we allow, or excuse me, this is the mixing percentage. I wish that didn't say regularization. Let me double check. I think this is showing it a little bit differently. Correct, this is the regularization parameter. Good. So, okay, yeah, because it goes to 0.1, not 1. And then this is the mixing percentages right here. Is this making a little more sense that this is your lambda, and we want ROC to be as high as possible? Does that make sense? And if you look right here, this is when ROC is the highest. ROC, which means we give the yes class a high probability. Awesome, Ben. Have a great weekend, man. ROC is the highest right here at this model that has an alpha. I can't go to that. That has an alpha of 1 and a lambda of 0.001. So this optimizes. So the whole point of the ToonGrid, which I'll make it a much easier ToonGrid to see. I'll make it a much smaller one. The whole point of the ToonGrid is to figure out what? The whole point of the ToonGrid is to figure out what? Like, here's a much easier one to look at. The whole point of the ToonGrid is to figure out the best what's to use. The whole point of the ToonGrid, because here's all the combinations. I've got 3 of these and 3 of these. Much easier to look at when there's only 9 things on the screen. But the whole point of the ToonGrid is to figure out the best what's. The whole point of the ToonGrid is to figure out the best what. Basically, which has the highest ROC, and then we just look at the combination right here to say, okay, which combination right here of alpha and lambdas are going to give us the best ROC. Does that make sense right there? Like, we're giving all these combinations, like we baked all of these cakes, and this was the best cake. So if we go to the more complex one, which was right here. This is the crazy complex one where I baked like hundreds of cakes. We have to zoom in a little bit to see what's really going on. And we can see this cake right here was rated the best cake. So these are just the ratings of the cake. Be very careful. ROC needs to be high. RMSE needs to be low, because this is a thing about the ratings or the rankings, the probabilities, excuse me. I was thinking cake rankings. But this is about the probabilities we assign, and this gives the yes class a higher probability than the no class, something like 99.87% of the time, which is pretty much all the time the yes class has a higher probability than the no class. And so this is amazing right here. So let's rerun the code, but with the other tune I did, because I think I overwrote it. And so there it is right there. And let's see if we get the same results. Oh, you see, you run it again, you get different results. Gotta love it. We're still seeing this area right here. And then let's find out which one's the best. The best tune is in alpha of 1. Okay, good. Yeah, I keep asking those questions. These are just tons of cakes. It's confetti cake. And so we have a lambda of 0.06. And so we're probably in this region up here. Let me zoom in a little bit. And lambda of 0.06, it says. It's a lot of very similar models. This is like when we were talking about today, there is no best answer. It's just going to be, you know, there's a lot of answers. The way I tuned this, we've got a lot of choices. Here's the results of the best model. There's the ROC of 99.86263. So there's one that's a little bit higher. Oh, is that it? Looks to be these over here. That looks to be it. And you see they're all super crazy close. It looks like that one's identical. So these two were identical. It didn't change any between those models. And we've got here the ROC standard deviation, which is our uncertainty. And when you look at this, the uncertainty right here is about 0.1, which puts all models, and this is what we're talking about today, all models from about here up are probably identical. Does this make sense, Trace, when I say since the uncertainty is about 0.15, and then it's more than that. So about 0.15. So if we're right here, really? Doesn't want to appear. It does not like me today. Let me play my sad music. Sure. All models from about here up are basically identical. Why are all models from about here up basically identical? Which is really like, I just kind of overly searched. I love to do those searches though. So why are all models from here up? Because I'm up here at an ROC of 0.9986. And then this is going down what from my best model? To say all those models are basically the same. Like they all have uncertainty. They can all work about the same. Not that their level of uncertainty is the same. They're all within one standard deviation. So what I'm highlighting right here with that number on the right that you can see is I'm highlighting, or the left of me, I'm highlighting the amount of uncertainty. I'm up here at the very top, like I'm moving the window where I'm at, and then I'm going down 0.15 in terms of percent ROC. So this is one standard deviation below my best model. Does that make sense, Trace? Like this is, all these models are probably pretty similar to my best model. So this is where today we saw in the notes, it's really a toss-up which one of these will work best on new data. So it's really just a toss-up right here. Now we go, and we can get the accuracy, not apply. What you doing? Oh, because variable name. What are you doing? There we go. I get 96.7% of predictions right on my holdout when I predict someone's gender. Post resample right here function. We need to put in our Y variable name. This is why I love this helper code. And there's the accuracy. It just does the same thing for us instead of computing it by hand. And then the ROC right here. Let's throw in the Y variable name. I think we got everything. Type equals true. And could not find function ROC. That should be in package. PROC. I'm going to have it downloaded. There it is. So it should get me ROC. There we go. And I'd say this is all right. It's close. On new data, it accurately predicts somebody's gender. It correctly ranks, because this is a ROC AUC. It correctly ranks the probabilities of gender 98.56% of the time. And the accuracy on gender when it was predicting someone's gender on the new data was 96.7. Pretty good. The coefficients, I don't really care for coefficients. Like, it goes in order of things I care about usually. So we can see right here what was used. Wow. That's all that was used. So cool. Makes perfect sense. Does this make sense that this is all the model used in predicting someone's gender? How tall are you? How much do you want to weigh? And what are your body piercings? That's all the information it used from all these variables. That is actually pretty beneficial in this one because it makes sense. This is how our model created and what it did to make the best predictive model it could in predicting someone's gender. Yeah, it makes perfect sense. Like, how tall are you? How much do you want to weigh? And then, how many body piercings do you have? And with this information right here, we can get a pretty accurate prediction. Makes sense right there. Getting a pretty good model. Yep. And then we get the non-zeros right there. GLM final model. And yeah, I think these are the non-zero, or these are the 0 ones. You know what's so interesting is that things like weight, yeah, so these are the ones that were zeroed out. Yeah. List the predictors that had non-zero coefficients if any are given. And then, yeah, we're getting the 0 ones right here. So these are all the ones that are zeroed out, and these are the non-zero ones. And yeah. Is it making more sense right here? This is kind of what you're doing, using the different techniques right here, making sure you're explaining them as we just walk through here and basically do, and this was a good example to kind of end on. This is pretty much today's lecture, but done with the code. So everything we learned theoretically today about the GLM net, which is the mix of the lasso and ridge, was done here in this code via the example. And once again, this right here, the training with R, the data mining carrot, has all the code set up. And I'd love to throw this into a Shiny app. I just don't code this every day. So I'm like, oh yeah, which thing do we use here? And just going through. But the format of the train function, so beautiful. Y tilde x comma data equals. And then what we can change this to, we'll have a different tune grid on this. But you could change this to like a k nearest neighbors. You could change this to a support vector machine. But the method, I'll show you this to end to completely blow your mind. If you want to go crazy, here's the list of all available methods in the carrot package. I think they still update this, but check this out, Trace. Here's the list of every single method you can use. Let's put on a little music here. Check it out. It goes on and 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 on. These are all the different methods you can use in the GLM, or not in the GLM, but in the carrot package. So would you validate and then make a GLM model to test the data? Oh, that's what we did. We did that. We did all of that. I'll show that again real quick. But if you go right here and type GLM, you can see there's even different types of GLM. Bayes GLM, GLM Boost, GLM right there, GLM. And there we go. Here's your generalized linear model right here. For classification and regression with no tuning parameters, we did GLM net. So we did GLM net H2O, GLM net, and there's so many things. There's all your GLM nets, elastic ridge regression. There's your mixing. There's your regularization. We talked a lot about regularization today, which appears really only 20 times on here. I'm shocked. Of course, decay can be a regularization parameter. So yeah, so many things inside of here. And so when did we see how it worked on the holdout? Here we go. So let me ask you this right here. How did we pick our model? Like, what are all these right here? If you see ROC, I know I don't know all those. When you see ROC and we picked the model here and you see this, our model was picked how? The model we picked out, which was our best model right here. If you look right here, we've got the GLM net results, and the model we picked was based on the what? And here's the answer of what it was based on. Like, this is where we're picking our model and we're seeing how it works on the what. So it's pretty much done for you because the GLM net is going to save your best model. And it's going to be, so the best tune right here is the best model, and that's what's saved into the GLM net Azure model. And that model was picked, that of the one that worked the best on the, and it was picked, it was evaluated on ROC. So ROC is like our metric of like, is it doing well? Let's look at its ROC. And then the data set used to create, or not used to create, but this data set used to evaluate, will this model work on new data is the Because I think you're asking, so would you validate it? This is the validation. This is the validation, and we pick our one model, and then this is the test on the holdout right here. So now we're testing it to the holdout right here. We're making predictions, a lot like we were doing today, where you make predictions, you enter the model name, the new data equals holdout. So does this remind you of what we were doing just a little while ago with the looping, where you go right here, predict your model, new data equals holdout, and then you go right here, this is classification, so we're seeing if it's equal to it, and then we're seeing what % of people in the holdout had their prediction equal to it. GLM, oh, I did type, oh, holdout not found. And so we're seeing what % actually matched, taking the mean of a logical vector. So the mean of the logical vector, you know, like, is somebody's gender in the holdout equal to the prediction RGLM? So let me read this. Is somebody's gender in the holdout sample logically equal to the prediction that the GLM net model makes on the holdout? Yep. And this is very, very similar to what we were doing just a little while ago over here. I think it's back right here. And that's what we're doing right about here. We're finding the residuals and we're predicting new data. And basically, what are we doing right here? If you think about this, we're tuning the model. We're kind of tuning it on the parameters. We don't have this in here anymore. But we were tuning the variables in the model by going through and looking at a grid of what's possible. And that's exactly what we're doing right here, is tuning it. Well, I think that's got it. Excellent work, Trace. Great questions. We will be back. I'm getting tons of random voicemails today. So when you're discussing why you choose a specific model, would logistic just be like, well, I choose it, why I kind of... Yeah, that would... So you could use logistic, but you would just be using... You could use like k nearest neighbors. You could use decision trees, like boosted models, but you can't use like linear regression. So you can't say, I'm going to predict a categorical variable and use linear regression. It's just that the techniques used in linear regression require a quantitative variable. But you switch to logistic regression, you're now doing a categorical variable. And that's kind of where our example started today, was saying, since we are doing a categorical variable, well, then we have to set everything up from the start to be a categorical variable. And the GLMNet, it's basically doing generalized linear models with the elastic net regression. That's what that stands for, generalized linear models with elastic net regression. I don't know why they call it elastic net regression. It's just lasso-ridge combination. And then you can see down here, we've got our GLMNet grid, which is just going to be the combinations of the alpha and lambda we are using. And then different models will have different tuning parameters based on, like, what do you think the k nearest neighbors tuning parameter is? Like, what do you think a k nearest neighbors tuning parameter would be? It's how many watts. And then we can like change it and be like, let's look at differences across here. And we should be able to grab a k nearest neighbors. Okay, so I got it. And this project is all about starting to make sense. Should we? Yeah, I think so too. Yeah, do a random forest, do a neural net. Yeah, and then look at the tuning parameters. And tuning parameters are just knobs you're changing. So on k nearest neighbors, there's only one knob. There's probably, maybe there's more. I can only think of one knob. Let's go here to nearest neighbors. Nearest shrunken. I don't even know what some of those are. Where's my nearest neighbors? K nearest neighbors. Yeah, sure. There's more. Kernel, depending on how you're going to measure distances. So kernel is going to control the measure of the distance. And really, I only really do that. And there it is. Oh, wait. Look. This is the one I use. It's like an advanced k nearest neighbors. And look, for classification and regression, what are they telling you here when they say for classification and regression with these? They're saying you can use it for a what variable or a what variable. This is starting to make sense. And you can go to, I won't take off if you try one of these and do something really awesome. I mean, try to do the ones we do in class, but this right here, I'll drop it in the chat. This right here shows you everything, and then it could be expanded upon. And the only parameter I really change around within k nearest neighbors is going to be the k. And someone else designed another k nearest neighbors, which can control the way we look at distances via the kernel. And then the distance, I'd have to look at how they're evaluating that. I do not know what that parameter is really going to control for. I want to know now. It's a method. It's a method. It says, nope. Is there documentation beyond this? That'll be a mystery to us. So we'd probably want to know what this method is doing exactly, but there's about 1 billion methods, not literally 1 billion, but you could do localized linear discriminant analysis. Discriminant analysis is pretty awesome. But if you're doing this, you can only use categorical variables. So with that, we'll head off here. We'll be back on Monday. Great work. Good practice here doing data analytics with time series and also data mining. I'll see everyone later. Bye for now. Bye.